All right. Hello, everyone, and welcome. If you've got a final exam on AI breathing down your neck, or you just want to get a real, hands-on understanding of one of the most important concepts in the field today, you are in exactly the right place. Today, we're building a Retrieval-Augmented Generation, that's RAG, pipeline, completely from scratch. We are going to go through the code, line by painful line, so you'll have everything you need to absolutely ace that test.
Okay, so here's our game plan. First, we'll dig into why we even need this stuff. What's the problem with regular old search? Then, we're going to get our hands dirty and build what's called a semantic library. After that, we'll figure out how to ask that library a question and get the right info back. And finally, we'll tie it all together to generate answers that are actually based on facts.
So let's set the stage here. We search for stuff all day, every day. So why do we need a whole new kind of complex system like RAG? Well, it all boils down to a massive weakness in how search has traditionally worked. I mean, just think about it for a second. How many times have you been searching for something, you know the answer is buried in some document, but you just can't find it? Why? Because you didn't type in the exact magic combination of words. That frustration is the exact problem we are solving today. And this slide just nails the difference. Over on the left, you've got keyword search. It's like a really strict, unhelpful librarian. If you don't give it the perfect title, it just says, nope, don't have it, even if the book you want is right there under a slightly different name. But on the right, you've got semantic search. This is the cool librarian who says, oh, I get what you're trying to find. It understands your intent, your meaning, and it finds things based on concepts, not just exact words. So here's the bottom line. RAG is our recipe for building that helpful librarian. Now, for your exam, you absolutely have to know these three phases. Phase 1, preprocess. This is the prep work. We chop up our documents into little pieces and figure out what they mean. Phase 2, retrieve. When someone asks a question, we go find the most relevant little pieces. And Phase 3, generate. We hand those pieces to a big AI model and say, okay, write an answer, but, and this is the important part, you can only use the information I just gave you. That's how we keep it honest. This is our roadmap.
All right, let's get our hands dirty with Phase 1, building our semantic library. This is where we take a normal, boring document, in our case, it's Apple's 74-page 10K financial report, and we turn it into this intelligent knowledge base that our AI can actually work with.
And the heart of this whole thing is something called a vector database. Now, don't let the name freak you out. A vector is just a fancy name for a long list of numbers that captures the meaning of a piece of text. So a vector database, it's just a library that's organized by meaning, where similar ideas are put on the same shelf. It's as simple as that.
For this project, we're using a tool called ChromaDB, and it's awesome for learning because, for one, it's super lightweight and just runs on your own computer, no complicated servers. It's also really fast, but maybe the most important feature for us is that it's persistent. That means it saves our work to a folder, so we don't have to reprocess and re-embed all 74 pages of that document every single time we run our code. Trust me, that's a lifesaver.
Okay, first lines of code. Let's break this down. That first line is us creating our database client. By saying persistent client, we're telling Chroma, hey, save everything you do in this folder right here called ChromaDB. That's how our work gets saved. The second line is really clever. Get or create collection does exactly what it says. If a collection, think of it as a table, called Ada Documents doesn't exist, it makes one. If it's already there, it just loads it up. This is a great feature that prevents you from accidentally redoing work or running into errors. 2 lines of code, and our database is officially open for business.
And before we start filling our library, what are we actually putting on the shelves? We're not putting in whole books. We're using these little chunks. The Apple PDF we're using has already been broken down into 453 of these chunks, and each one has not just the text, but a ton of rich metadata, like what page it's from, whether it's part of a table or just regular text, and even its exact XY coordinates on the page. This extra info is going to be super valuable later on.
And here we go. This is the engine room of the whole pre-processing phase. We have to create a loop that goes through every single one of those 453 chunks, one by one, turns its text content into a vector, and then carefully stores it in our ChromaDB library. This loop is literally what builds our entire knowledge base.
Okay, let's zoom in on a most important line of code right here. Inside that loop, for each chunk, we're making a call to the OpenAI API. We pass the actual text of the chunk as the input. We tell it which model to use. Text embedding 3 small is fantastic for this. The API sends back a response, and we have to dig into it a little bit to get the vector itself with .data.0.embedding.
The result, which we're storing in a variable called emb, is a list of 1,536 numbers. That's the vector. That's the numerical fingerprint of that chunk's meaning.
So once we have that vector, we have to store it. We use the .add command on our collection. And notice we're giving it a few things, all as lists. We give it the embeddings, that's the vector we just made. We give it the original documents, which is the text itself. We give each chunk a unique ID so we can find it later. And we give it all that rich metadata. This is so critical. You store all of it together. The embedding is for the search, but the text, ID, and metadata are what you actually want to get back. We do this 453 times, and then our library is full.
Okay, phase 2. Let's see the payoff. Our semantic library's built, it's populated, all the books are on the shelves. Now, how do we actually ask it a question and find something useful? This is the retrieval part. So we're going to hit it with a real-world question. This isn't just looking for a keyword. We're asking a conceptual question about a specific number in a specific year. Let's see if our system can understand the intent behind this question and go find the right data inside that massive 74-page document. So what happens under the hood? Well, this is the really cool part. It's perfectly symmetrical. First, we take our question and we do the exact same thing to it we did to all our document chunks. We turn it into a vector using the same OpenAI model. Then we just ask ChromaDB, hey, can you find the chunks in your library whose vectors are the most mathematically similar to my questions vector? Finally, we can filter out any really weak matches and just return the best of the best.
And would you look at that? The results are amazing. What's so cool here is that top hit. With a similarity score of over 0.4, the system found a table on page 35. Our question didn't say find a table or look for iPhone sales. It understood that net sales was a numerical concept, and it correctly identified a table chunk as being the most semantically relevant piece of information. That right there is the magic of semantic search. It works.
We've built the library. We've retrieved the right information. Now for the grand finale. Let's put it all together to generate a nice, clean, human-readable answer. This is the generation part of Retrieval-Augmented Generation.
Now, to make this last part really easy, we're going to use a framework called LangChain. It basically automates this whole process for us. So the user asks a question. Our retriever, which is our ChromaDB system, goes and fetches those relevant chunks we just saw. Then LangChain packages it all up with a set of instructions and hands it to a large language model. The most important instruction is, you must answer the user's question using only the information I'm giving you right now. And the code to do this in LangChain is shockingly simple. First, you set up a prompt template. That's basically the instructions for the AI, with little placeholders for the context we retrieve and the user's question. Then, you initialize your LLM, your language model. Finally, this one magic function, create retrieval chain, just wires everything together. It takes our ChromaDB retriever, pipes it into the prompt, and then pipes that into the LLM. It creates this one neat object that handles the whole flow. And there it is, the final output. The chain took our question, it found the relevant data chunks, and it synthesized them into this perfect, concise answer. It's accurate, it's to the point, and most importantly, it is completely grounded in the source document. The AI didn't make this up, it simply summarized the evidence we provided.
So let's just recap the whole thing. Think of this as your study guide for the exam. To embed, we used OpenAI. To store, we used ChromaDB. To retrieve, we used Similarity Search, and to generate, we used a LangChain RAG chain. Each piece of the puzzle has a very specific job, and now you know what they are.
So, we've done it. We've built a working RAG pipeline for one document. But that leaves us with one final big picture question. You've got the core logic down now. So how would you take this and scale it up? How would you build a system that could handle thousands of documents, automatically processing new ones as they come in? Thinking through that question is the next step to building real production-level AI systems. Thanks so much for joining this explainer.